An experiment is conducted to measure the specific heat capacity of water. A mass of water is placed in a glass beaker and energy is transferred from an electric heater. The data collected are mass of water, change in temperature of the water, energy transferred from the electric heater. First of all, notice that how to write the calculated to the measured value correctly. This plus minus is the absolute uncertainty, should be rounded to one significant figure. And since it's thousands, the value also must be rounded to thousands. So it is rounded to this digit. Here it's just 0, but it is rounded to this digit. For the second, you can see that plus minus 0.5, so it's to tenths, so it is rounded also to tenths. And this example, you can see it's plus minus 300, so it is rounded to 100. It can be rewritten like this: 16.0 plus minus 0.3, it's correct. But 16 plus minus 0.3, it's a mistake, it's not correct. So 16.00 plus minus 0.3, it's not correct. So the first question, calculate the specific heat capacity of water, just using a formula. It is given in the data booklet, and it's what energy Q is equal to what? It's Cm delta T, where C is the required specific heat capacity, M its mass, delta T change in temperature. We can calculate the required specific heat capacity. And notice that if you meet change in temperature, you may use degrees Celsius or degrees Kelvin, it doesn't matter. But if you meet just temperature, then must be in Kelvins only. Because Kelvins are SI units, not Celsius. So we need just calculate it, and it's 16,000 divided by 0.250. And notice that it's not crucial to write 0 at the end. You should just take into account that it is given to 3 significant figures, and change in temperature is 14.0. And we need just calculate it, and it is equal to this value. I will round to 3 significant figures due to general rules of rounding. For multiplication or division, keep such number of significant figures as least precise. So I will write 4,570 joules per kilogram per Kelvin, but it may be per degree Celsius, it doesn't matter. But here you may write just unrounded value. It's not crucial, it doesn't matter, because our aim is finally to write specific heat capacity and its absolute to the appropriate number of significant figures, and it's crucial. Here it doesn't matter actually. And the next question is determine the absolute uncertainty in the specific heat capacity. What is absolute? It's delta C. And first of all, relative or fractional or percentage, it's actually the same. It's absolute divided by the value. And it can be given as a fraction or decimal, and it's called the relative or fractional. If you multiply by 100%, it becomes just the same value in percent, and it's called percentage. But for if there is some formula, and if there are plus or minus, so addition or subtraction, there is the rule in terms of absolute uncertainties, and it says that the resultant absolute uncertainty is the sum of absolute uncertainties. And if you need relative, then you calculate relative. For multiplication or division, there is a rule in terms of relative uncertainties, and the resultant relative uncertainty is the sum of relative uncertainties. And if you need absolute, you then calculate absolute. So there, for our problem, we can see that there is division and also multiplication, so we can calculate relative or fractional delta C over C firstly. And notation for relative, it's absolute divided by the value, so it's just delta C over C, and it is equal to the sum of relative uncertainties, so it's delta Q over Q plus delta m over m and plus delta t over delta t. Don't get confused, delta t is just a name, and it is equal to delta q. It's what? It's 300 over 16,000 plus delta m. It's 0.002 over 0.250 and plus 0.5 over 14.0, and we get just decimal. Here, if you multiply by 100%, you get like percent, and it will be called the percentage uncertainty, and you can see that it is equal to this value. Again, I will just round to 3 significant figures because everything is to 3 significant figures, but it's not crucial here. You may write just unrounded, it doesn't matter. So it's 0.0625, and you can see that relative has no units. And then delta c can be calculated as a value. It's c multiplied by delta. It looks like this: c multiplied by delta c over c, and you can see that c cancels, and you get delta c directly. So it's a value, and I will use the exact values. It's 4571.4 and so on, multiplied by the relative uncertainty 0.06246 and so on, and we get this. And again, I'll round to 3 significant figures, but you may write as unrounded, it doesn't matter, it's not crucial here. And absolute has units, so joules per kilogram per Kelvin. And finally, write down the specific heat capacity of water and its absolute uncertainty to the appropriate number of significant figures. Here, rounding is crucial, so delta C absolute must be to 1 significant figure, so it must be plus minus 300, and then the result also must be rounded to 100, so it's 4,600 joules per kilogram per Kelvin, or it's 4.6 plus minus 0.3 kilojoules, or times 10 to the power 3 joules per kilogram per Kelvin. The next, outline one source of systematic error in the experiment and its effect on the calculated value of the specific heat capacity of water. In general, what is systematic, how to remember or how to understand, not with respect to this problem in general. For example, if you use a balance and when you, it's also called zero error, and for example, you measure, each time you measure, for example, 10 grams, you get each time 10 grams greater than actual value, and it's an example of systematic. So for this problem, for this situation, what can be systematic? You remember for such type of problems, there always are what? Losers to surroundings, and hence we can write what? That energy transferred from water or from the heater to surroundings as an example of systematic error. Surroundings, or water evaporates, or it's the same as we can say decreasing mass of water. And what about the effect, how it works? For example, 100 joules are provided by heater and 90 goes to water, and 10 joules are lost to surroundings, but C is calculated using this 100, but actually water gets less value, 90 joules, and you can see that C is directly proportional to Q, so calculated value is greater than actual, or actual is less, and we can say that our calculated value will be overestimated value. It means calculated is overestimated. You may just write directly that the calculated, it's actually meaning of overestimated, so you may say just overestimated and it's enough, or say that the calculated value is higher than the real value, or the true value, or the accepted value. It's actually the explanation of overestimated. If you say overestimated, it's not necessary to explain what it means. So overestimated value, or the calculated value, is higher than the real value. And that's all for this question.